Good day and welcome back to Chemistry Videos with me, Clarissa Sorensen-Unruh. We are going to talk about nuclear chemistry today. Kind of an introduction to nuclear chemistry, which is great fun. Most of chemistry deals with the rearrangements of reactants to form products. And basically the idea we have is that the reactants fall apart, their bonds break, and then they are kind of mixed together in a new way and new products form, okay? But the quintessential piece of most of chemistry is that the reactants and the products have exactly the same elements. That's how we can balance equations, so on and so forth. Nuclear reactions are such that you do not have the same elements on the reactants and product side. You have different things, okay? Because actually the nucleus decays usually. Decay is a word we use with nuclear chemistry. And so you usually have something radical happening at the nuclear level and the nucleus, and that changes the nature of that element such that it's a new element. Awesome fun. Okay, so what we're going to do is we're going to balance nuclear reactions as well. Basically what we're going to do is we're going to have, if you have the elements that are reactants, right? Those basically have to be the same as in the products. Now, what am I saying is the same here? Obviously, it's not the elemental symbol. So what I'm saying is that the sum of the A's of the reactants, everything on the top, if you add all of the reactants together, the sum of all of those atomic masses, remember that atomic masses are symbolized by A's. We could also talk about those. Really, what we would say for this is it's not even atomic masses. That might be a misnomer with the book you're using, which actually means atomic weight, which is the weighted average of the isotopes masses as they exist on the planet Earth. That's a whole different thing. This is really more of what we call the mass number. That might be a better way to think about it. So the mass number is the number of neutrons plus the number of protons. That's really what A is signifying, okay? It cannot be a decimal or a fraction. It has to be just a whole number, okay? This is the atomic number. Z is the atomic number, and that's just the number of photons. Okay, so when I balance a reaction, what that means is the sum of the A's of the reactants have to equal the sum of the A's for the products. In other words, if I add all of the mass numbers of all of the products and all of the reactions together, they have to equal the same number. Okay, so it equals where the arrow is. The sum of the atomic numbers of reactants have to be exactly the same as the sum of the atomic numbers of the products as well. Okay, so in other words, the tops up here have to, if you add those together, have to be exactly equal to the tops added up over here. The bottoms, the atomic number have to be, if you add those up together on this side, have to be exactly equal to the bottoms added up over here. Okay, so that's what balancing a nuclear reaction means. Okay, so there are multiple kinds of nuclear reactions. Let's talk about each of them. All right, so alpha decays, which happen anytime the atomic number is greater than 83. Okay, and there are beta decays. That happens anytime the N to Z ratio is greater than the band of stability. So we're going to call that 1 if Z is between 1 and 20, and greater than 1, more than 1, if Z is greater than 20. Okay, the highest this gets is about 1.5, and I've talked about that in other videos, but it gets at about lead, it's about 1.5. So it's not going to get, it's not like it gets to 2 or anything, it gets to about 1.5. Okay, so that's kind of what beta decay is, or how we predict it at least. There's positron emission. And electron capture. And both of these happen at the exact same time, which is really fascinating. Both of these happen when the N to Z ratio is less than 1. Okay, so if the N to Z ratio is less than 1, and this is again, if Z is between 1 and 20, so if the atomic number is between 1 and 20, which ends in about calcium-ish, then you have about, the band of stability is about 1 for the N to Z ratio. And as you get higher and higher and higher, the N to Z ratio gets to about 1.5 at lead, which is about as stable as we get, the last really stable isotope that we have. Okay, so both of those are exactly the same in terms of how we predict what it is. Okay, now let's talk about what this actually is. What does an alpha particle look like? An alpha particle is basically a helium atom. We could label it like that. We could label it like an alpha particle. You just write alpha and write 4 over 2 He, it's a helium atom. Or we could write 4 over 2 alpha. All of those are possible, right? So let's take something that's going to decay in this way. Let's give you an example of what this looks like. In terms of what it looks like, I put away my periodic table. Well, that was brilliant. I'm going to use my phone. Did you know that there are periodic tables on phones? I have apps for that. It is fabulous. There's an app for that. Let's do something. You're kind of picking out whatever your favorite higher than 83 moment is these days. Let's do Roentgenium. Oh, that's cool. Yeah, that's cool. Okay, let's do that one. Rg. Rg has one isotope. It's 272. You can always tell these that are man-made because they have the atomic, or the mass, the atomic mass or the atomic weight in parentheses, which means that they're man-made and there's only one isotope of them. And it has an atomic number of 111. Okay, so we know that this is going to alpha decay. Let's do alpha like this, just to be fun and interesting. All right, so there's my alpha. What I need to do is I need to ask myself on the side here, I'm going to do it in orange. Okay, 272 has to equal 4 plus some number. And I also have to have 111 equal to 2 plus some number, right? So what is the number here? 272 minus 4, I'm going to move 4 to the opposite side. 272 minus 4 is 268, if I'm not mistaken. And 111 minus 2 is 109. And then I look up on my handy dandy app because it's still here and still with me. I love apps for that. So cool. I look up what happens, what element is at atomic number 109. Oh, and it's meitnerium. That's awesome. So we went from the scientist that discovered X-rays to Liesl Meitner, who is never given credit for a lot of things that she did in chemistry, particularly in terms of nuclear chemistry. Awesome. All right, so that's MT. Awesome. And that's cool. What this is called, by the way, is this is called a daughter nuclide. And sometimes this is called a parent nuclide, just as an FYI. The funny thing about this is that apparently we only make daughters, not sons. So I don't know why that's true in nuclear chemistry, but it's true. And so in terms of looking at this, this is how we predict what we're going to make in the end. Okay, and obviously meitnerium is absolutely unstable just as it is because its atomic number is still greater than 82 or 83. And so it will alpha decay as well, which is how we get nuclear reactions that happen one after the other and after the other and after the other, which is called a chain reaction, if you have ever heard that term. And that's what happens in nuclear facilities. Okay, let's do a beta decay. We did a beta decay with something the last time I talked about this, which was nickel. Okay, nickel is going to undergo a beta decay. Okay, what does a beta particle look like? Well, I said it looked like this. Beta particles can also look like, so basically like alpha particles, they could just be labeled beta, or they could be labeled 0 over minus 1 beta, or they can be labeled 0 over minus 1 E. Now, what is all of that talking about? What that's basically talking about is that a beta particle is a high-speed electron. So you're basically ejecting a high-speed electron in the midst of this. And what happens when you eject that high-speed electron is that it effectively changes a neutron into a proton, which is cool. So cool. So cool. So what am I going to do here? I'm going to do the same thing I did up here, right? So 63 has to equal 0 plus some number. 63 plus 0 equals 63. And what number plus minus 1 equals 28? Well, that's subtracting out a 1, right? So 29 minus 1 equals 28. And we know that 29, when we have an atomic number equal to 29, that's actually copper. Okay? Awesome. Positrons. Positron emission. Emission is basically the same thing as decay, so sometimes you'll hear this in the same context. A positron emission, positrons have to be one of the coolest things we talk about in terms of chemistry, beginning chemistry, because it's the first time we've talked about antimatter, which is great, right? So if a beta particle is a high-speed electron, a positron is exactly the same idea. It's still labeled B often, but with a beta, but it's actually a plus 1. So it is the exact same idea, the antithesis, the antiparticle to this high-speed electron, which is a beta particle. So cool. Okay, so that is not labeled as beta, by the way. If you just see a beta, that's a beta decay. Okay, it has to show the plus, and you can label it like this, or you can label it like this. And that's basically the two ways that it's labeled. Okay, so antimatter, matter and antimatter, so much fun. We know that if antimatter and matter collapse or hit each other at just exactly the right moment, they collapse. That's kind of what happens in terms of the high-speed accelerators that they're doing. I knew I had that word somewhere in my brain. All right, awesome. So what are we going to use for positron emission? We're going to use one of the best isotopes for positron emission because it's used in positron emission tomography, which is otherwise known as PET scans. Fun. All right, so in terms of this, we're going to have 15 over 8. That's oxygen 15. It's an isotope of oxygen. We can already see that its N to Z ratio is less than 1, right? So if you subtract out from 15, 8, you get 7. That's what N is. N is the number of, I never write that somewhere. N is the number of neutrons. And it comes from subtracting A minus Z, gives you N. So in this case, I have 7 neutrons, 8 protons. My N to Z ratio is less than 1. So I'm going to have a positron emission. Ooh, there it is. So to predict the daughter nuclide, what number plus 1 gives me 8? That would be 7, right? And what number plus 0 gives me 15? That would be 15. Makes kind of good sense, doesn't it? And that still is not perfect. Because in terms of looking at this, right, you have 7 plus 8 equals, or 7 plus 1 equals 8. 15 plus 0 equals 15. While this was less than this was an N to Z ratio of less than 1. You now have an N to Z ratio greater than 1, which means that this is probably going to undergo a beta decay immediately after. Kind of a crazy idea. Okay, but this is the daughter nuclide, and 7 is indeed nitrogen. So that works out kind of nice for us. Fun stuff. So oxygen 15, positron emission. Let's do the same exact thing with electron capture. Because oxygen 15 is still an N to Z ratio of less than 1, right? So an electron capture, what capture means is that it is a reactant. It goes on the reactant side. So it's still going to be an electron. It's going to be symbolized just like these guys over here, usually with the electron moment. So usually you're going to just do 0 minus 1 E. That's usually how it's shown. But it's going to be on the reactant side. It's the only one that is a reactant. And so then you do 8 plus minus 1 equals 7. 15 plus 0 equals 15. And that's still nitrogen, right? Either way, you made nitrogen as a result of this process, which is why both of these accomplish the exact same thing. They give you the exact same nuclide in the end. Okay? The last kind of nuclear chemistry is one of the more dangerous types, and that's a gamma decay. Gamma decays usually happen in the midst of everything else. There's not a specific reaction. There's not a really great way to predict this decay in terms of having it happen. You can almost always guess that it might happen along with like an alpha decay, but not always. And gamma particles can be shown as gammas. 0 over 0 gammas, that's pretty much the way that it's shown. Okay. Gamma particles, what are gamma particles? Oh, no, actually there's one more way that this is shown. Before I go crazy here. It can be shown with an H nu. What is a gamma particle? A gamma particle is a high-speed photon. It can be a photon. It can also be considered just kind of energy. Because it has no charge and no weight, it essentially can penetrate by far the most from a nuclear reaction. And gamma radiation is what tends to kill people pretty well. Okay, so just FYI, that's not a pretty moment, but it is part of the deal that comes with nuclear reactions. Okay, so in terms of this, what are we going to do? We're not going to do an example of a gamma decay simply because they're hard to predict. Okay, if you see a gamma decay, recognize that it has no mass number and it has no atomic number, but otherwise it's going to be accompanying something else. Okay, so in terms of that, here are the 5 decays for nuclear chemistry. Until I see you next time, I bid you adieu.